Hi everyone, I'm Felienne. I'm also on Twitter, so if you're on Twitter and you want to talk about this talk, you can mention me so I can read what you thought about it later. Is there a hashtag for DomCode as well?
DomCode.
It's DomCode. So if you want to talk about the venue or the food, not me, then you can also use hashtag DomCode. And as Ross already said, some of you might know me from my spreadsheet fame, but to avoid any disappointment, this talk is not at all about spreadsheets. So if you came here for this, I'm really sorry. I'm going to talk about programming by calculation today. That's making a program not by just thinking what it should do, but by using actual math. But before I start, let me ask you something. This is the first time I'm doing this talk, and I will at least do it 3 times more at other meetups and conferences. So it's totally fine to ask questions in the middle, and it's also totally fine if you are lost. If I'm not making any sense to you anymore, then please let me know. You know, sometimes they say if you see something, say something. For this talk, I would like to say if you don't see something, say something. So just feel free to raise your hand, even if you don't have a question, if you're just somewhat lost, because I have 250 slides and there are like 10 pictures in it, and the rest is all mathematical equations. So I'm pretty sure if you are lost, you're not the only one. You're just a little bit braver than some other people that might be lost. So as a service, not only to me, but also to all the other people that have to endure that horrible avalanche of mathematical formulas, let me know if something is unclear. I have a whiteboard here, so if I need to do some additional proofs just from the hip, I can do that. So let me know if you're lost, please. Oh yeah, and if you want to look at the slides, if you prefer to look at the slides instead of looking at me live, the slides are already on my website. So you can go there and download them and look at them if that's what you like. So, normal programming. This is how normal programming looks like. You start with a problem, then you get very frustrated and you think very hard for a long time, and then suddenly you think, oh, I have an idea. I know how to do this. And then you have a program. That's, I guess, how most of your work days look like. Most of mine also look like this. This is program derivation. This is way cooler than normal programming because you start with a problem and then you write a specification. And you're still happy because you're just writing a specification. And you take your specification and you derive a program, which is fun because you're doing maths and nothing on the computer yet. So you're still having fun. And then by doing the derivation, you end up with a program. And you see, no frustration, all happiness all the way. No angry people. But also, not just not angry people, also not the light bulb moment. You don't need to wait for divine intervention to come up with your program. You write your specification, and then you play with your specification until you have a problem. That's program derivation. Let's start super simple. We want to sum a number of numbers. So we want to sum the numbers from 0 to n. So how does that look like? What you might think now, because you're still in the thinking angry programmer mode, you go to the keyboard and you type something, maybe a for list or a link statement. But no, you know now, we want to have a specification. So this is how a specification of a simple sum could look like. We have something called a result, that's a variable, and what we want is the sum of all the i's, all the variables I, between 0 and n, and this is what we're actually summing. So you see the I is a little bit repeated there. That's because we could also want to sum all the squares of I or all the roots of I. So here is what we're summing. So what you could do with this specification, okay, secretly I'm now going back to the computer, is you can use a resharper on the specification. You can do this. Look how familiar that looks like. You probably will do this often in your life. You can say, hey, I have a constant here called n, but I would like to refactor this constant and introduce a parameter, because I don't want to just sum all the numbers between 0 and big N. I want to sum an arbitrary number of numbers. So you're familiar, I think, with the operation I'm going to do now. I will take a constant and turn it into a variable. That's how it looks like in ReSharper. I want to name my parameter little n, and then in ReSharper you would get this. This is what happens if you turn a constant into a variable. You get a nice little parameter there called n, and our big N is replaced by a little n. And of course, we don't really like that name result. So we're going to call it up to n, because that expresses a little bit better what we're doing. We're summing all the numbers up to the number n. That's now a small n. And of course, if we somewhere in our specification had a variable that referred to that thing that used to be called result, what resharper automatically does to your code, so this magical specification resharper version also does that, is it replaces it with a call to the function that we just made. So that result that we were summing is now called with the input of big N. So nothing really changed. We took our specification and we generalized it into not just summing from 0 to big N, but from 0 to small n. And this process, here repeated again, is called replace constant by variable. And this is a famous program derivation technique. If you have a specification, if you want to solve something for a specific number, well, you might as well derive a program for a variable number. It will help you. And not just it will help you derive, but also now you can solve your problem for arbitrary n's. So you probably already, if you use ReSharp, who's a ReSharper user here? Who's a C# dev? Oh, not that much people. But Eclipse has these refactorings as well. You already know what I'm talking about. It's just the same operation, but in the context of specifications. So what we want now, here's one of the pictures. So enjoy it, because there are not a lot of them. What we want now from the specification is we would like to have an implementation. We want to have a program that actually sums it, because I promised in the end the result will be the same. We will have a program. So what we can do is we can distinguish two different cases. We can see, because we have a list of numbers, there can be 0 or there can be n more than 0. So we can start with 0. What does up to of 0 look like? So we take the definition of up to, here it is. To remind you, this is how up to look like. We say, well, up to n is the sum of 0 to n. To n with n. So we can plug that here, but of course now, because this is up to 0, we replace the n with a 0. Everyone still there? Awesome. This is okay. So now we see that in this domain, from 0 to I, but also smaller than or equal to 0, there's only room for just one I, which is 0. This is a singleton domain. There's only one in it. So we can say the sum of I, 4, we can replace this with I is 0. It's the only I in there. Now, because I can only be 0, I can replace all those I's with a 0. So we get the sum of 0, which is, using some math, this is highly advanced university level mathematics, this is 0. So we know now, if we put in 0, out comes 0. So far, probably still doable. What we can also do, of course, is now we think about the case of the sum of up to a random n not being 0. This will be important later. The n is not 0. This is the alternative case. So we do the same thing. We just calculate. And this is where the not idea bulb comes in. I just take the specification. I'm not thinking. I'm just mechanically applying rules I know. This is a rule I know. I can input the specification. So we get the sum from 0 to and with n. Another rule we can apply, apart from the take a big N and replace it by a small n, is we can look at this. I is smaller than or equal to n. That is the same as saying, this arrow means if this holds, then also that size holds. So if it's true that I is smaller than or equal to n, we can say, well, either it's smaller than n, or it is n. That's more or less the definition of smaller than or equal to is smaller than or equal to. And we can exploit that, because we can say, well, let's split out those two possibilities in different parts of the calculation. So we can say here, either I is smaller than n, or I is equal to n. This is a situation we already encountered when we had I is 0. There's just room for one n. That's easy. That's equal to n. Oh, there's a plus sign lost there. Now here we can do something else. There. If I is smaller than n, That means it has to be true that I is smaller than or equal to n minus 1. Because either it's something smaller, and then it's smaller, or worst case, if it's the highest thing that still fits in smaller than n, it can be equal to n minus 1. So if this is true, that must also be true. That's again sort of the definition of smaller than. So we can use that, and we can transform this guy into that. It's smaller than or equal to n minus 1. And now something interesting happens. Some people might have, I see some happy, smiling, nodding people. That looks like someone we know. Doesn't that look exactly like up to n? Well, almost. Let's look at the definition again. This is the same. The only thing that's different is I've now substituted n for n minus 1. So I could say, hey, that's the up to of n minus 1 and n. And I told you in the beginning of this part of the derivation that it was important that n was bigger than 0, and this is why. Because if n wasn't bigger than 0, we wouldn't be guaranteed safely to apply or to call up to n minus 1. Because n could be 0, and then we're calling up to minus 1, and that is undefined. That's outside of the scope of our specification. So, we have an implementation for the up to function. Because up to n is, well, if n is 0, 0. And otherwise, if n is bigger than 0, we just call the up to of n minus 1 plus n. So without thinking, we've made a program. Someone has hidden something. And this is, of course, how it looks like. Suppose you would run this program on a machine. If you would call the up to 5, then using the definition, you could say, hey, that's the up to of 4 plus 5, and you can see how you could be able to construct a machine that could execute these type of specifications. If you really insist, you could even type it into a computer, but it's not really needed because we've proven that this program is correct. So why would we spend time on executing it? So some people say, yes, but this is very easy. I could have come up with this program easily. That's true, but maybe some of the other programs in my talk, that will not be true. But also, again, you can only come up with such a program if you are willing to go to frustration state, if you're really willing to think really hard about how your program should look like, whereas this was zero effort. You just take the specification and you manhandle it until the program comes out. You don't need divine intervention. And I will show you a few other examples, still within the realm of some, that are pretty hard to come up with, but easy to derive. Oh, a question.
Can I make a program to make this program?
There are programs that make programs from specifications. Not necessarily yet in the context of functional programming, but there are proof assistants where you can put in a specification, and a little bit like ReSharper or refactoring tools in Eclipse, you can take a specification and apply things from the library like replace a constant by a variable, do a range split, but it's always human assisted. So you have to tell it, hey, apply these rules, try a few, because obviously this is a very simple program that you could automatically derive, but the choices that you make can be, you have to explore a big state space, and some experience with programs, knowing what tools to use is useful. Who of you is familiar with F#? Ish. Okay, not that many people. So the code examples that I will show there are not a lot, but they're all in F#. But as you can see, it's pretty readable even if you've never done F#. But this is how, if you're insisting on implementing the program, you could implement it in F#. Let is defining something. This rec keyword means you're defining a recursive function. You have to tell the compiler you're doing that, otherwise it won't work. You cannot make a recursive call. A question?
Yeah, you said we don't deal with negative numbers in our specification. But, I mean, why doesn't that just mean that your specification is incomplete?
That's very much true. I just declared that out of scope. You could, of course, here add a construct. You can add two things. You could either say, I make a type, and I make a type that's only positive numbers, including 0, and then you could say this function only works on that type. So then you limit you limit people expressing it. Or you could add a construct here saying, well, if it's -1, then undefined. But yeah, you're right. The specification, I just specified it for n's between 0 and whatever you want.
But you made it sound like it was a conscious decision to keep negative numbers out of scope.
Yes.
Isn't it entirely possible to just not think of it if your specification gets more complicated?
That's a very good question. So how do you know your specification is right? So secretly, maybe in my whole string of happy people, there are also less happy paths. So you can, and there will be examples of this actually in the talk where I will show you that, you pick a certain specification and you end up with something else. So it can be a correct program that isn't very efficient. It can be a correct program that isn't very beautiful. Or you can end up with a program that's correct for all the options you tried, but you failed to see one option, and then the program fails for that reason. That's very true. So this is how a program looks like in F#. You can say if n is 0, then 0, and else we do a recursive call. But what you can also do in F#, which is even nicer because it looks more like our derived program, is you can do this. You can do pattern matching on your argument. You can say match n with 0, this is very equal to an if. And this is if n is 0, then 0. And if n is something else, then you do a recursive call. The nice property of this now is that you can use the n, the same name, instead of an else. But in programs a little bit later in my talk, you will see that n can also be more complicated constructs. So you can do a little bit more advanced pattern matching, and then your programs really look like your derived programs, which is a nice property. So, ta-da! We have an implementation. This is how it looks like. But of course, what we could also do is start from the beginning of the list. Because I just did some hand waving and convinced you that we should start with that big N. But there's another constant in our specification. Yes, enjoy this, because there will be more math coming. So there are two constants. And of course, a natural thing is to immediately look at the big N as a candidate for replacement. This is one of the things I said. If you've done these problems often, you think, oh, that's a candidate for generalization, but we don't have to. We can also pick 0. We can say, well, I want to refactor this constant that's not a variable name, but just an actual constant. And you can do this in ReSharper as well. You can pick a constant and make that into a variable, a real constant, a number. And then you get a from function. From n is the sum from I. It's overall I from little n till big N. This is an exercise for you to derive the program from. So if you're watching this talk later on video, you can now pause it and go to your sketchbook and actually do it. Or if you see the slides on SlideShare. But also if you're here, of course, later on, forget I showed you this. Close your eyes for 30 seconds and then you can still do this as homework. Yes? Homeworkers, close your eyes. This is the implementation. So we say the from, if we're at the end of the list, like if we were at 0, it's 0, well, if we're already there, it will be 0, and otherwise we just we do recursive calls all the way back. Which is nice. It's a mathematical implementation, but if you try to type this into F# or your favorite programming language, you'll see that not all constants are created equally. Because if you want to define the from n, well, here it is. We want to match n with, big N. Oh, yeah. Where is the big N? I mean, I could type it, and actually F# lets me type it. So I can type this. I can say match n with big N. This will just work. Because that in F#, that big N is just a variable name. It's just going to match n with another variable. So unfortunately this does work, although the compiler tries to warn you here saying, well, this big N will match with any value you want. Because how the pattern matching works is just, hey, is N equal to a random other variable name? Yeah, sure, no problem. So you can type it and it will type check with a warning, but of course this is not what you want to. So here you already see that while both the specification is the same, but because we make a different choice, we somewhat end up in trouble, even though the program is fine. It's a tad harder to implement this. Of course it's possible, you can define a class with a field big N and you can use that. It's possible, but you see the choices here that you make in program derivation matter. Something else that we can do, if we take a step back and instead of immediately diving into picking a variable, let's look at the pattern here. So we're going to do the same. We use the definition, we do a range split, and then we end up with this. This is what we did in the first derivation. And we just split off N, and we end up with this. What we did in the first derivation is we said, hey, that looks like up to. Bam! Let's use up to. We can do that. But of course what we could also do is, instead of that, not immediately make a decision on seeing up to, not being greedy and think, that's an up to. I can do a recursive call and I'm done. We can continue. We can say, well, let's split. Let's split some more. If you repeat this, you eventually end up with no sum anymore, but just a list of 0 to all the way to N. So by repeatedly applying the range split, we're now just summing all the values, but we have pluses in the middle for all the values. And now we have somewhat delayed our choice of doing a recursive call. We're already here, but we're still in the situation that we can go two ways. Either we go this way, and then we end up with the second program, or we go that way, and then we end up with the first program. So sometimes it's beneficial not to immediately think, there's a recursive call, but to calculate a little bit more, because potentially another program will come out. And that's what happens now. So why don't we have both? We started at the beginning, we started at the end. Could we do both of them? Could we chop off numbers from both sides of the array? Well, of course, I wouldn't be showing you this wonderful GIF if that wasn't true. So we can do a super sum. We're saying we're generalizing on two sides of the array, the beginning and the end. So here, this is the M and that is the N. This is the definition. And we can split that, just as we did in the beginning or the end. I guess you're getting the hang of it, so I'm taking the pace up a little bit. We can do that. Split the range. And now here on either side, we have on the one hand side an M falls out, and on the other hand side an N falls out. And we can split that again. So now here we have, I think there's something wrong with my slides. Here we replace the from to. So this is a recursive call. On the one hand side we add 1, and on the other side we subtract 1. So now we have M plus from to. And we can do this again. So here we do the same thing. We're delaying our choice. We're not immediately saying, this is the from to. We're saying, well, let's try it again. Let's split once more. And now you see a pattern. Because here we have an M and an N. But here we have an M plus 1 and an N minus 1 on the other side. So with just a little bit of mathematics, I can reshuffle this formula. And then it says this. 2 times M plus N. Because this and that is an M plus N. And that is an M plus N. And what's left is the rest of the sum. With on both sides, now we have 2 numbers chopped off. If we repeat this a little bit more, so again we resist the temptation of doing a recursive call here, because we could, but we're not gonna. We can repeat that, and then we do this a number of times. Well, how many times do we do that? N minus M divided by 2, because this range, well actually this range, is N minus M long, And for every call, we get 2 numbers. So we have n plus n times n minus n divided by 2. And now you see we don't need any recursive calls anymore. We can directly calculate the sum of the numbers from n to any number from 0 to big N, or from 3 to 150, whatever we want, without any recursive call. So delaying the choice that we make is beneficial because we don't need any recursion. Obviously, this is a very efficient solution because it's order 1. I didn't invent this, unfortunately. This guy invented this. He's called Gauss, and he already invented this when he was in elementary school in the 1700s. And unfortunately, he didn't do program derivation. He just looked at all those numbers and he thought, hey, those two look the same, and those two, it's exactly the same, and then you can sum it. As legend has it, he got this assignment in elementary school because he was being annoying and the teacher wanted to punish him. And then he responded by being more annoying by solving the problem in like 1 minute. But the nice thing I think here is that this is a stroke of genius. I mean, this guy obviously was brilliant and he made great achievements in mathematics in later life. But we don't necessarily need to have that stroke of genius if you just play with the specifications, which, as I showed you in the beginning, is a happy and enjoyable thing to do anyway. In the end, you might come close 300 years later to the genius of some mathematicians. So let's make things a little bit more interesting, because, summing the numbers between 0 and a big N, that's a bit easy. Apparently people can do that in elementary school. So let's look at a function that searches values. We're going to define a function called contains, in which we can put a list and an integer, and that function will produce a boolean that, from the name, I guess you can guess what it does. But let me specify it precisely. The contains of a list and an integer is equal to, this thing is called exists. That means there exists a. So there exists a x within L, that's that guy, that is equal to y. So it's just a fancy way of saying the list L contains the value y. There is a value x in L that's precisely equal to y. So this is a specification of what the contains means. So we can calculate with that because we now have a precise specification. So does the empty list contain y? Let's take a vote. What will this be? Does the empty list contain y? Is there an x in an empty list that is equal to whatever y? No. Who says no? That's nice. You're all still with me. So we use the definition and we use some logic and we all come to the conclusion that this is not the case. That was the easy part. Now we're going to look at a list that looks like this. So remember in the sum, I said, well, we're either taking the 0 or we're taking an n that's bigger than 0. I'm doing the exact same thing. Now I'm saying either I take an empty list or I take a list with a head, that's an element of the list, with behind it some sort of tail. So this is the equivalent to n is bigger than 0 because this list is not empty. This, if you pattern match this in F#, and I will do that later, it will not match with an empty list. It's a bit tricky, the definition, because T can be empty. It will match if you have a head glued to, concatenated with an empty list, but it won't match for an empty value in an empty list. So we have our definition. Here it is, in case you forgot it. There is an x in, well, we're replacing the y with head on top of tail, for which x is equal to y. This is just the definition. So with the sum, I didn't really tell you that, but you saw that when I split the range, the sum split into a plus. So I chopped one without really telling you what I did. I said, if I take 1 out of the sum, it will go to a plus. That's because a sum is secretly a repeated plus. Well, an exists is secretly a repeated disjunction. Because if there has to be one of the elements in the list for which this boolean is true is this one, or that one, or that one, or that one. So in a similar fashion to splitting the sum into pluses, I'm now splitting the exists into the disjunction, into an or. Is that clear for everyone what I'm doing here? Yes. Awesome. So either my x is within this list of h, or it's in the tail. And look at this difference. This is important. This h, the type of that h, of the head, is an element of the list. So in this case, it's an integer. This is why I have the brackets around it. Because there must be a list here. X in h would not type check, not that I have a type checker in PowerPoint, but it would not type check if I had one, because h is an element and you cannot inspect if something is an element of an element. So what I'm doing here now, this notation means assume that h is equal to y. So if I write such a square with a line next to it, that means in this scope, h is equal to y. So I'm just saying, let's assume for a moment that this is true, and let's explore what happens in that case. So in the case that h is equal to y, there I can do something. Because there exists an x in y for which x is equal to y. Well, I have such an x. So I can eliminate an exists by giving you an example. Like, is there someone in this room with, let's say, a blue and white blocked shirt? Well, there is one, because look, he's right there. Wave to the audience. Yes. You see, so there exists one in this room is now true, because I have presented you with one example. That's what I'm doing here as well. Look, there is such a y. Why? Because it's right there. It's actually been hiding amongst you, disguised as h. Look, it's right there. So that's easy. I can say it's true because, as you can see, it is there. And this part, of course, is unaffected. We don't know anything about the tail. But with a little bit of math, and this is still, I think, understandable, true or something is true. If I already found one, then we can stop. Great. So that's one part of the equation. On the other hand, the alternative is if h is unequal to y. And here, it's quite easy to see now that our specification is complete, because either it's h or it's not h. But you're right, that's not always easy. So we can do the same thing, but now eliminating the exists into something else. Because we know there's only one h there. So suppose I would just take this sir here, by itself, we put him into a list of integers, and then we look, a list of people wearing shirts, and we look at him, is there in this very limited list someone with a white and blue blocked shirt? No. We only have to expect this one little integer to see that that's not true. So we can easily say, well, that's false, and whatever is still left there, using some super advanced mathematics, that will lead to
the right-hand side.
The right-hand side. Thank you. I didn't instruct him at home at all. The right-hand side, because we already have false or something. Well, the false is definitely not going to save the day, so we need to get our truth value, if possible, from the other side. And then, this is someone we know. Hello. There exists an x in the tail for which x is equal to y. That is the contains of ty, of course. Because we're now inspecting, well, I don't have the definition anymore, but we're now inspecting only the tail. And this leads to a program. I'm not implementing it anymore. So you can see that either it's h or it's not h. So suppose now we're not anymore looking at random lists. We're looking at special lists. Lists that satisfy this. the is ascending condition. This is potentially where I lose people, so let me know. What this says is, a list is ascending if for any, this is for all of the elements in, it's the little brother of exists, for all elements I and j within the list, so smaller than the length of the list, if I is smaller than j, then the element at position I should be smaller than or equal to j. So if I have a list, if I take an element here and an element there, this element must be smaller or equal to this element. So that's a very fancy, precise way of saying this list is ascending. Suppose now, like I did before, I want to define a contains. A contains with two sub-lists. What I can do now is I split the list. It's exactly the same as what I did before in the range split. And I say either the x is in the first sub or the x is in the second sub. So I split the range up, but not as I did before by chopping off one little element from the beginning, but by chopping it right in the middle. Or, like, actually, secretly I'm not specifying where I'm chopping it, but I'm chopping it somewhere close to a potential middle. Suppose now, again here we're saying suppose. Suppose we have a p that is equal to the last element of the first sublist. This n here, that one, is the list of elements in sub 1. So I'm taking the last element of the first half, the first subset of sub-list of our list. So now, again, I can look at different options that could be true for that element p. Either full specification, it's equal to p, y is bigger than p, or p is bigger than y. These are the three options that we have for integers or other comparable values. So if p is equal to y, I'm not going to do the whole derivation again because I think you got the hang of it. Then we can say, well, look, p, he's right there with his white and blue shirt. We don't have to look any further. In those cases, p is smaller than y or p is bigger than y, we just get our original specification back. Because so far, we don't know anything yet. However, we can do some math. Again, this is what we call raising a flag. So I say, I am now declaring with a flag here that sub 1 is ascending. That if I split this list into two lists, and the full list is an ascending list, I'm now just waving with my hand and ask you for 1 minute to believe that if I have an ascending list and I split it, the first part is also ascending. I'm just going to assume you believe that. I will prove it later, I promise. For now, we're just going to assume that's true. Suppose it's true that that first list is ascending. We have a p, like I had in the previous slide. We have a p that's the last element of that list. And this is our definition of ascending. Again, for all elements I and j in the list, if I is smaller than j, the element of L at I, in this case our L is sub 1, is smaller or equal to the element of j in sub 1. Just is ascending applied on sub 1. What we can do now is called instantiation. So I'm saying, if it is true that for all of these j's, this is true, I can pick a random person, a random integer, and it will be true for that person. What is the minimum age in this room? Let's try. So if I say, is everyone above 30? Is everyone above 30? Who's not above 30? Oh, wow. Oh my god, I'm so old. Who's not above 25? You serious? Okay, who's not above 10? Let's cut this crap. That makes me feel slightly worse, actually. Okay, so we're all above 10, and that is great. So I can now point at a random person, that person there with a purple sweatshirt. You're above 10, because you're one in this room where everyone is above 10. That's, I guess, easy. So I'm looking at that J. Let me just pick a J that happens to suit my proof very well. That's N. So you see this for all now is only quantifying over, oh, there should be a J there. But now not anymore, it shouldn't be there now, because this for all is now only ranging over i's, because I fixed the J. And I fixed it in such a way that J now is equal to N. But that's sub 1 of N, we know that. We know that by another name, because it is secretly P. So we can take that and substitute the sub 1 of N, the last element of sublist 1, and replace it by P, because P is equal to sub N1. Ta-da! So what we have now is, for all I in sub 1, if I is smaller than N, sub I is smaller than P. And that's just a fancy way of saying whatever is in sub 1 is smaller than P. We're going to call this rule 1 just because it won't fit here if I need it later. So this is the situation we're in. So we did a sub here. We haven't made a choice on P anymore. Yet, I mean. We haven't made a choice on P yet. We're just calculating, suppose P is equal to sub N. Now we're looking at what are we actually doing. Let's go back to the three options we are exploring. Well, this option is finished. We already have an implementation there, which is P. So now look at this option. Suppose we're calculating over that option. So we raise another flag, and we're saying P is bigger than Y. It's one of the three options we're looking at. In that case, this is just a copy of the specification. Nothing secret is happening here. Let me go back. I'm just copying this. So I'm just saying if P is bigger than Y, we don't know anything yet. Just the specification. Now we can use rule 1. Because we know for everything that is in sub 1, all i's in sub 1 will be smaller than or equal to P. So we can say, well, that P here, it will never be there because all that is in that list is smaller or equal to P. Whereas in this part of the program, we have assumed that P is bigger than Y. So we can look at that room, like we can look at this room, and try to find someone below 10 years of age. They won't be there. We already know that. So this is false. And then this stays the same. So it's just false or something, which is something, yes, with some super advanced logic. So we could scratch out half of the list, in case we're splitting equally, because we know P is bigger than Y. So here, we can just scratch that out, because it will never be there.
Shouldn't it actually be true? Because P is bigger than Y, and the element in I is smaller or equal to P, so there may actually be...
No, have I tried the wrong option? P is bigger than Y. And for everything that's in sub 1, everything is smaller or equal to P.
So there may be in X that's equal to Y. In sub 1, because everything in sub 1 is smaller than something that's bigger than Y.
In case you're right, it's very hard to determine if you're in front of a room, but in case you're right, then these two things should be swapped. So then obviously that goes there and that goes there. But you can delete half of the list by looking at the right side of the bigger than. But, as I promised you when I started this, we still have something to prove. Because I just, said magically, well, if a whole list is ascending and I split it somewhere, then those two sides should also be ascending. I just said this is true for one of them. But I didn't prove that. I just said, suppose it's true, then look at this magical proof. But we still have to prove that. But luckily it's not that hard, because we can say, well, we have a list. This is the definition. And now here again I substitute the whole list for this. So instead of the is ask of L, I have the whole list here. What I can do with a for all is, if it's true for all people, it will be true for a smaller subset as well. So if I split the room here, all these people will still be above 10. Because it's for everyone, so I can just take whatever subset. I can take one person, but I could also take half of the room. So we can do that here as well. I can just say, well, I'm only looking at the first half of the list, or the first sub 1, however big that is. Still true. Now here, I'm saying I want to have the ith and jth element of two lists concatenated. That is equal to taking the ith element of the first list. As long as it's true that all the elements are smaller than the length of the element. So as long as I'm looking at elements smaller than the length of the first list, I can say I'm just inspecting that first list. And luckily I know it's all smaller. Because here I've limited myself coincidentally to exactly the first list. So that means I can take elements from the first part of the list, same element as the whole list. So suppose this first row is the list. This is the first half of the first row, and this is the second half of the first row. Element 1 of the first row is equal to element 1 of the first half of the first row. As long as I'm only looking at the first half, as long as I'm smaller than the beginning. So I can do that. I can here substitute sub 1 for the substitute of just sub I. Well, now look who's there. It's the definition of is ascending, but just on a little bit smaller list, exactly the list sub 1. So now I've proven that if a whole list is ascending, the first part is also ascending. And with a little bit more, I'm not going to do that, but with some more homework, with a little bit of more, it's a bit harder because you have to shift the dummies to the bigger side of the list, but you can also prove that if a list is ascending and you split it, then the second half will also be ascending. So, we've done search, now let's do some sorting. That would be nice too. So I'm defining a function called allElements. And that function, it doesn't say here, but it goes from lists to sets, or from lists to bags. So I have a list, and all the elements will be an unordered set of elements. So for the empty list, I get the empty set. For a list that only contains of element B, I get a set of element B. And all the elements of the concatenation of two lists, S and then T, is S plus T. And that plus here is a plus on sets. So it's not adding to integers or strings. It's adding a set of things to another set of things. You can also use a plus for that. Some people write a union there. So here's our friend from the previous example. I guess you expected that that would be back. The is ascending. What I showed you before, a few slides ago, was if ascending is true on S and then T, ascending is true for S, and ascending is true for T. Pop quiz. Are these things equal? So it's true. It's definitely true that if this is true, then that is true. Is it true the other way around as well? If this is true, is that true as well? Is it equal? Why not?
Because the element of S can be bigger than the first element of T.
You're very right. I can have 4, 5, 6, and 1, 2, 3, and then both subsets would be ascending, but gluing them together won't be. Very good. Happy that some people are still there. If we add this, and I'm not going to prove this, but I guess you can see that if I add this, it will be equal. If this is ascending, and that is ascending, n. This says for every b in S and c in T, so every pair that I take from ST, b will be smaller or equal to c. If I add that, I exclude the case where I have 4, 5, 6 and 1, 2, 3. Yeah, just like, trust me. And if you don't trust me, that's fine. You don't have to argue with me. You can just send a proof. Make a proof. Send me on Twitter a screenshot of your proof. Actually, in one of my other talks, I solicited proofs. I said, hey, here, you can prove this. And people actually on Twitter made handwritten proofs and texted me pictures of it. So, if you don't believe me, send me a proof. 10 more minutes. What we would like to have now is a function called sort. And it's defined as follows. If I have a list, for any list I can think of, if I sort it, all elements should still be there, and I would like sort L to be ascending. So this definition is a bit different from the definitions we had before, where we said this sum is exactly to this. What I'm saying now is, I want a function that specifies this. So I'm not, that satisfies this. So I'm not saying sort is this. I'm saying I want a sort that looks like this, that has these two properties without repeating the whole specification. But if you want to say it in natural language, you would say you're not stealing elements and you're putting all of them in order. That's what it says. So what we can do here, like we did with big N and small n, we can take this list and try different options. And for now, we're only going to look at this part of the specification. So I can say, well, we're not stealing elements. How does that look like? Well, if I have an empty set, there's nothing to steal. That would be true if it would be the case that sorting an empty set is the empty list. So this is true. What I have to satisfy here for the empty list is true, only if it were true that that is true.
Wouldn't it be empty list sort is the 0 with the line?
No, because I'm sorting a set that's unsorted, and what comes out is a list that is sorted.
Okay.
If I'm sorting one element only, well, how could I do that? Suppose I would have a set that just has one element. We make the list of one element. That's easy. Now, suppose I want to sort the set of things S and T. Again, here we say S and T should not be empty. Just like in previous examples, we're splitting in a way where the sets are smaller. This is what we want. Well, how can we obtain that? Suppose here, indeed, S is smaller than L, and T is smaller than L. And L is the whole thing. So we're splitting in a way that both sides at least have one element. Then I could say, I'm sorting S, and I'm sorting T, and I take elements from both of them. Because both are smaller. This is like a recursive call on S is n minus 1, because n minus 1 is smaller than n. Now, here I'm stuck. I don't know what to do anymore. And this is maybe one of the most important things to remember from this talk. If you're stuck, push your proof obligations further. So I don't know what to do, but let's just imagine I have this magical puzzle thing here. Suppose I have that. It just fall out my sleeve, a puzzle, and that just specifies that. I'm just saying, I will define it. Why not? I'm in charge. I'm defining that. Now, if it would be the case that the sort of S plus T is equal to the sort of S puzzle thingy sort of T, then this would hold too. So instead of deriving a program immediately, I'm deriving the conditions of things that should hold. So here I now have a specification for my sort, and I have a puzzle thingy that needs to make this true. So it needs to be the case that the sort of S plus the all elements of sort T is equal to the all elements of puzzle thingy. Now we're done. Look at that. We have a sorting algorithm. Because if L is empty, it's the empty list. If L is, this should be curlies. If L is curlies, we get a list of B. And otherwise, we just take puzzle here. Ta-da! We're done. we just need the plusly thing. And it needs to specify this. That's exactly this transition. So it has to be this. And in the previous part, I only looked at that. So to save some time, I already knew at this point I might be in time trouble. We're not looking at that. But if you do the same exercise on the second part, you will get this, which is, as you can see, quite similar to the first part. So you get another additional rule for the plusle thing. These two things have to hold. That's what we need, a plusle. So what about conjunction? Concatenation. We take two lists and we just merge them. Suppose we take that as a plusle. So I'm not deriving it, I'm just taking something. Well, they're sort of similar. The one is a strange plus and the other is also a strange plus. So let's just see what happens if we pick list concatenation. This is just a choice. These are the two rules that we need for a plusle to be correct. So we can use rule 1. Where's my rule 1? Oh, I don't know where my rule 1 is. Here it is. I knew it was coming. So I have a conjunction of two lists. That's the definition of is ascending. If I concatenate two lists, then this must be ascending, that must be ascending, and everything on that side must be smaller or equal to everything on that side. That's the definition of is ascending. And I can use that here. So this is just a repetition of the definition of is ascending. As you can see here, this is pretty easy to prove. Because if this is true and that is true, well, yeah, that's also on the other side. So it's very easy to prove. If I start in a situation where A and B is true, and I have to prove A and B and C, well, the A and B are already there. That's very easy. So now just this is left. I have to prove that for every B and C in S and T, everything in this side is smaller than everything in the second list. So a quick hack I can do, I can just move that to the other side. So I can say, suppose we're in a situation that I have two lists, and all the elements of this one list are smaller than all the elements of the other list, and both of them are ascending, well then I can just merge them. And so this is an easy sorting algorithm. Suppose you have two lists, and both are sorted, and the one is smaller than the other, well in that case, you might as well just concatenate them, because you're done. So what you could do is this. This is a very nice sorting algorithm. Yes, I can put the concatenation instead of the plusle, but then that has to go, but I just change it into this. Now this sir is going to say, that is not a complete example, because there will be some examples that you will encounter where your sorting algorithm has to work on something else than two lists that are already sorted in the right order. That will happen. I can guarantee you that there will be cases that will happen. So we can just fix this. We can just make it so that our concatenation will only work on lists, two lists, both sorted, and the one is bigger and the one is smaller than the other. We can define a function called partition, and we just say, well, we use a partition. And how did the partition look like? Well, what partition will do for you is it will make sure that all the elements in this list are smaller than all the elements in the second list. And in that case, suppose that is true, well, we can just merge them. Suppose only we would have a part that would do that would give us two lists from which the one is smaller and the other is smaller, well, then we can just sort the two of them and we're done. So I'm not going to prove it, so I'm just going to impress you with quick examples. Here's a part that will work. You can prove this at home. You can prove that this part that I'm showing here, where you take the median value and then your division in the two lists is everything that's smaller or equal you put on the one side, and everything that's bigger you put on the other side. You can prove that this part specifies that. And now we have a real sorting algorithm that actually also works on lists that are not already sorted. Here it is. Are people recognizing this?
Quicksort.
Quicksort! Wonderful! We've just invented quicksort. Isn't that nice? Can I have like 5 more minutes because then my entire set will be over?
Okay.
Cool! So this is how it looks like if you want to type it. Again, we have a match. We have an empty list. We have a list of lists. And indeed, secretly here, I'm now sorting lists instead of bags because it was easier implementing. And if our list is anything other than an empty list or a list of one element, well, I'm just going to split this list up into lists. I will sort both those lists and then merge them together. And this is how part looks like. So part is, I take the sum of the list, I divide it by the length of the list, which is, well, the average, not exactly the mean. That's the type of distinctions you run into when you start implementing things. The mean versus the average. So this is an implementation, and then you filter that list U on everything that's smaller than the median and everything that's bigger than the median. You give them back to the sorting algorithm, and that goes to sort both sides. So that's super nice. I have a sorting algorithm, but I would like to have another sorting algorithm just because I have to get examples. So suppose, for reasons of efficiency or clarity or just reasons for I'm curious what can happen if I play with this specification more, I just want one recursive call. I don't want 2, I just want 1. I'm greedy. So, can I do that? Can I make a puzzle where I have one element and then the sorted rest of the list? Is this possible? Well, I can see what happens. So I'm just going to add a rule to the specification that the length of S should be 1. Just a rule. I can make the rules. So let's see what happens. We're going to say S is 1. We have the same sorting and we still have to abide by the same puzzle rules. So I'm sorting S and I'm sorting T and I'm puzzling them together. Because the length of S is now 1, this is just, I've scratched out S. So this is now just S and the sort of T, because that was what I wanted to do. So the length of S is 1. That means there is exactly one thing in that list. Let's just call that thing B. Because the list is only 1 long, there is a B, there must be something in that list. So let's say whatever is in the list is B. There must be a B that's in the list. So I can say the list of B plus the sort of T. Now, instead of the puzzle I had before, I'm now going to introduce a timesel. That's a times with a circle around it. So I'm just going to say, well, this puzzle is a timesel. Again, I have pushed the obligations I need to specify further. I'm not going to make a decision now. Well, in this case, I'll make the decision like 3 seconds later. But normally, you can do some more calculation and say, okay, I will deal with that timesel whatever time comes. Time is now. So, I need a puzzle for which it's true that if T is ascending, timesel. If T is ascending, and I timesel B to T, the whole thing is still ascending. That's what I need to specify the conditions of the thing formerly known as puzzle, now known as timesel. Well, that's not very hard, because I can timesel B to a list. Oh, this should be B. If I timesel B to a list, it will be B. And if I have a B and I have a list consisting of a head and a tail, how do I make sure that that whole thing is ascending? So I have a list and a B. Well, suppose B is smaller than the first element of the list. Then it's pretty easy to make it sorted, assuming the rest is already sorted. I can just put the B in front. So I have a list of things, let's say 3, 4, 5, and I want to timesel 1. Well, I just put 1 in the beginning. If the rest is taken care of, 1, and then, what was I saying, 3, 4, 5, it's fine. So if the first element is smaller, I just glue the B in the beginning. Suppose it's not the case. Suppose I have 1, 3, 5, and I want to timesel 2 in. Well, it's not going to go before 1. at least one is going first, and then the rest of the thing can deal with the 2. So if b is smaller or equal to h, I first put h, then I put b, and then I times all the rest. This algorithm is also known as... I just heard mumble sort. That's cheating. No, it's actually insertion sort. So you take an element and you put it in the right place, step by step. So this is how it looks like, by the way, if you implement it. And here, I promised you, I still had a proof obligation, because I promised you that sometimes pattern matching can be more powerful than just a variable. And this is here how it looks like in actual F#. So I can say a list is empty, or a list is one element, or a list is something and then the tail. And then I can actually calculate with both the head and the tail. So I can write things like that, and in other programming language it would be a bit harder, because you have to get the first element and then do some list magic. But here you can just say, well, that list, I'm redefining that L now as something in the beginning of something else, and then you can use those two immediately as a variable. So I've here now called, instead of times all, called the thing insert. So I'm inserting h in the sorted tail, and then this is how the insert looks like. This is really exactly, well, with some small light substitution, this is exactly what we derived. So you see that F# and also other functional languages are very close to how you write specifications. It's very easy to write something like this, where you do list manipulation. So what we've proven now, which is quite, I think, a nice insight that I otherwise wouldn't have had, is that insertion sort is a special case of quicksort. So first I've derived quicksort, and then I say, okay, I add this one little restriction, and then using the same techniques, I get a different sorting algorithm. And we really have to stop, but there is the similar way of proving that selection sort is a special case of merge sort, and then quicksort is a special case of merge sort as well. So merge sort is like the mother sort, and then you have two subcases, quicksort and insertion sort, and selection sort is if you add two other conditions. I think I will write a blog post on that. So this is everything for today. A few takeaways. Programming is math. I know programmers that say, yeah, I love programming, but I'm very bad at math. Like, how is that possible? Programming is math. Okay, I'll make it a bit weaker. Programming implies math. So it's not the case that math and programming are equal, but at least programming has some math in it. But also, of course, creativity and design and other stuff. But math is a big component. So calculation provides insight. So something like I showed you, this is a special case of that. You see that by calculating. I'm definitely not advocating that you should all, before writing any line of code, add some proofs, because that's not very plausible. But for some cases, it does give you new insights that you didn't have before. Specifications matter. So the way you write something down is influencing the code. And I think the simplest example of that I showed was if you're summing and you start at the beginning or you start at the end, your code will look radically different, because if you start at the beginning, your class needs an extra field big N, because otherwise you can't do the summing. So writing things down precisely from the beginning is really helpful in knowing what will happen to the code. And if you practice this, you will definitely get better at seeing a specification, and like the proof sort of jumps at you and the program jumps at you because you know a few of those tricks. And something else that I think is also important and applicable in general, delay choices where possible. So it's fine, I think, if you're programming and you're saying, well, I don't know how this will look like, let's just shelve that for a bit. And I know if you're actually implementing, that's not very realistic, because compilers won't let you do stuff you don't really know. But when you're designing or talking about a solution, don't settle on things if you're not sure yet. Just work on the things you know and then figure the rest out later. So one thing I should definitely show you is I know all this stuff because of this guy, my retired professor in Eindhoven, Rob Hogewoord. I just wanted to say thank you. I stole all of these proofs from him in lectures I had at university. That was it. That was my talk, Programming by Calculation. Again, I'm Felienne. I'm Felienne on Twitter. If you want to ask something, you can send me a tweet. Or maybe we have some time. 2 minutes or 2 questions? 2 questions. You pick, Ross.
Is there a good way to deal with side effects?
No, functional programming. Can I have another free question? Because this was no, that's a fake answer. There are similar techniques for imperative programming. So related program derivation techniques also exist for imperative languages. The structure is different though, because instead of taking a specification and really calculating with it, what you usually use is invariants. So you have, for instance, a loop invariant or a class invariant. And you calculate, for instance, for the summing, you could have an invariant for a loop over sum program that would be the variable I have now is equal to whatever I was summing up to now. So it's very much var x would be equal to the up to I had up to n. And then you can prove in every step of the iteration, this will be true if I increase I increase my variable with n as well. And then the loop makes sure that this invariant remains true. And then, at the end of the loop, it holds. So this is possible. This is the brand of programming by derivation that was argued by Dijkstra. But, yeah, no one really does that. Well, no one does this either, but this is at least closer to programming than that. But it's very true. There's a very similar related field, and that's programming derivation for imperative languages. There was one more question I could have, too.
Yes, I was going to ask about getting paid to modify state in my program. If I'm the only one...
Well, if you want to modify state, monads.
Don't explain them to me, then I don't understand them.
And I won't understand them anymore. I thought that was the deal.
F sharp instead of any other functional...
Oh, yes. Oh, that's...
What gave you this choice?
Yeah, that's a very easy question. There are lots of good answers to that. What I personally like about C# versus F# as opposed to programming language where you can mix both styles, like Scala and some people say JavaScript. I made a refactoring tool that has a front end in C# and a back end in F#, and I really like to move between those worlds. I'm doing on-click events and null checks and the horrible things that you just have to do in a user interface. And then I transform everything into wonderful, clear representations of, in my case, parse trees of the things I was refactoring. And then you send that to a beautiful, wonderful world with rainbows and unicorns and no side effects. And there you do the heavy lifting like this. You do parsing and tree transformations and stuff where you really benefit from a strong type system that does not allow you variables and side effects. And then you're done. And then in our case, we make the parse trees back into strings, and then we send the strings back to the horrible, ugly reality world. For me, I really love that over mixed style because I am a very undisciplined person. So, give me variables, I'll be like, okay, like, just this one variable. Okay, a tiny bit of state. I will, no. It never happens, and then you end up with, yeah, you could do it functional, but it's one big mess. So, I personally really like unicorns, garbage. Division between those two. But I guess that's really a personal opinion because I know there are people that argue the other way around. Yeah, that was 2, so that's it. Oh yeah, go ahead.